Hello friends, welcome back. So today we are going to study about the next process, that is the constant entropy process. It is also called as isentropic process, or it is also called as the adiabatic process. So today we are going to discuss about the different parameters of the constant entropy process or the adiabatic process. Then we'll solve numerical on this process. So, what is the actual definition of this process and what we are going to consider in this particular ideal gas process, that is the constant entropy process or the isentropic process, or it is also called as the adiabatic process. The process in which entropy of the gas remains constant during expansion and compression is called as the isentropic process or the adiabatic process. Now in this case, the entropy of the gas or entropy of the system is assumed to be remaining constant. So when the entropy is going to remain constant, we know that entropy is a function of heat transfer. Therefore, whenever there is no heat transfer between the system and the surrounding, so whatever is the entropy of the system is there, that entropy will remain constant. So what is the requirement for a process to be a constant entropy process or the isentropic process? The requirement is that there should not be any heat transfer between the system and the surrounding. Therefore, when we don't want to have the heat transfer between system and surrounding, so we are assuming that we are having the system which is having the perfect insulation. So we can see here in the figure on the slide that we have considered a piston cylinder mechanism. So 1 kg of gas we can see here for the analysis. We are calling it as a system, and we are enclosing this particular system by a perfect insulation that is shown by the hatching lines. So this is a perfect insulation is there, piston cylinder mechanism, and an ideal gas of 1 kg we have considered here. So the dq or q, that is the heat transfer between system and surrounding, is considered as 0 here. Then and then only we will achieve this condition, that is the constant entropy process. Entropy will remain constant. Now practically it is not possible to manufacture or to produce a perfect insulation. Therefore this is a totally ideal gas process. This is an imaginary process, just like the other processes what we have seen in the previous lectures. Now for this analysis, what we are considering here, so we consider a arrangement of the frictionless piston cylinder arrangement as shown in the figure for this particular process. It is assumed that there is no heat transfer between system and surrounding. Therefore dq is equal to 0 for this process. This is assumed to be a perfectly insulated process or perfectly insulated system. The process is represented on PV diagram and the TS diagram. So we can have the two type of processes, that is the constant entropy processes, that is the constant entropy expansion process and constant entropy compression process. Now, so we have represented this particular process on PV and TS diagram. So from the initial state point to the final state point, so we are going along this particular line, that is the expansion process, where the pressure is decreasing when the volume is increasing. So we are having this particular random curve. Now neither of the parameter is remaining constant. Just like in the constant temperature process, the temperature was constant. In the previous cases, the volume and pressure was constant. But in this case, all the three parameters, pressure, volume and temperature, they all are changing. And pressure, we are knowing that it is inversely proportional to the volume, and temperature, that is directly proportional to the volume and pressure, that is by the Charles law. So on the TS diagram we can see the constant expansion process we have represented here. So we are getting a vertical line here. So from the initial state point 1 to state point 2, so during the expansion process, as the pressure is decreasing, volume is increasing, and pressure and temperature are directly proportional. Therefore temperature is decreasing here. temperature is decreasing during the expansion process, but entropy is not changing. Entropy is equal, that is S1 is equal to S2. So we are getting a vertical line here. So from step point 1 to 2 in the expansion process, so entropy S1 is equal to S2, but temperature is dropping from T1 to T2. Similarly, for the compression process, so we have to provide the work energy to this particular piston, then we can have the compression of the gas molecules. So when we are compressing, we are decreasing the volume, your pressure is going to increase along this particular curve, and temperature is also going to increase. So pressure and temperature are directly proportional. Therefore, when we are decreasing the volume, we see that the pressure is increasing, temperature is also increasing, but entropy is remaining constant because heat transfer between system and surrounding is zero. Now we see that the expansion, isentropic expansion and isentropic compression is carried out along this particular process curve, which is obeying the governing equation, that is PV to the power gamma is equal to constant. Just like PV is equal to constant was the governing equation for the constant temperature process, but in case of the isentropic process, our governing equation is PV to the power gamma is equal to constant. So pressure and volume are inversely proportional, but one more important term is introduced here, that is the gamma term, and gamma is nothing but Cp upon Cv of that particular gas. So Cp is the specific heat of the gas, and Cv is the specific heat of the gas at constant volume, and Cp is the specific heat of the gas at constant pressure. So gamma is equal to a ratio of Cp and Cv. So gamma is equal to Cp upon Cv. So that is the important term, and this gamma value is going to remain constant because Cp and Cv values are always constant for that particular gas. So this gamma term is introduced in the governing equation, that is PV to the power gamma is equal to constant. So for this particular isentropic expansion and isentropic compression, during the isentropic expansion, whenever there is an expansion of the gas here, so we see that the heat transfer is zero. So whatever the internal energy is there of this particular system, that is utilized for the expansion process. So that much internal energy is utilized, and we see that expansion of molecule takes place. Piston is moving towards the right hand side. We are getting the work output here. So we are having the work output on the expense of the change in internal energy, because we are neither providing the heat or neither rejecting the heat. Therefore heat transfer is zero, but whatever internal energy is there of this particular system, that is utilized to produce the work in the isentropic expansion. But during the isentropic compression, we are having the reversal of this process. So whatever work we are supplying here, we have to supply the work input for the compression. So piston moves towards the left hand side, compressing the gas, and the internal energy of the system increases, temperature of the system increases, enthalpy of the system increases. But as there is no heat transfer, the entropy of the system is remaining constant. So during the compression, the work energy is totally converted into the internal energy, and during the expansion, internal energy is totally converted into work, as heat transfer is zero. According to the first law, the total conversion of energy takes place between only work energy and the internal energy for the isentropic process. So this analysis we will see in the next topics, that is the analysis of the process. So first parameter for analysis is PVT relationship. Now as we are knowing that in this case, that is the constant entropy process, all the three parameters are changing, they are variable. Pressure, volume and temperature are changing. But we are knowing that what is the required condition for the isentropic process, that is the dq is zero, heat transfer is zero, therefore the entropy is remaining constant. So when S is equal to constant, then PV to the power gamma is equal to constant. PV to the power gamma is equal to constant. So this is the governing equation for us. Then P1 V1 to the power gamma. So we are applying this governing equation to the state point 1 and 2. So we can write P1 V1 to the power gamma is equal to P2 V2 to the power gamma. Therefore, writing in terms of the volume ratio and the inverse pressure ratio, we can write P1 that is V1 upon V2 to the power gamma is equal to P2 upon P1. So we can write this as V1 upon V2, putting the gamma term to the right hand side, so it becomes that is equal to P2 upon P1 to the power 1 by gamma. So we can use this particular pressure and volume ratios in the during solving the numericals to find out the pressure and volume terms. Now we are also knowing that temperature is also a variable parameter, it is also changing. Therefore, by doing the complicated derivations, by solving the complicated derivations in the thermodynamic analysis of this process, we are getting a generalized equation which is giving the relationship between the pressure, volume and temperature for the constant entropy process or the adiabatic process. So this relationship we can use to solve the problems. That is T2 upon T1 is equal to P2 upon P1 to the power gamma minus 1 upon gamma, that is equal to V1 upon V2 to the power gamma minus 1. So this relationship gives the ratio of temperature, pressures and volume with each other. So this is the generalized equation giving the relationship between the pressure, volume and temperature. So we can equate any two ratios and find the unknown parameters in terms of pressure, volume and temperatures while solving the numericals. Now second parameter is the work transfer. Now we know that work transfer is given by W is equal to integral P dV. So after solving this derivation, what we are getting the final equation for the work transfer for the isentropic process, that is equal to P1 V1 minus P2 V2 divided by gamma minus 1. So we are going to use this particular equation. So we can write this equation in terms of the general gas equation also, that is P1 V1 we can write mRT1 minus P2 V2 we can write mRT2. So mRT1 minus T2 we can write this equation as mRT1 minus T2 divided by gamma minus 1. That also relation we can use to find out the work transfer. Now change in the internal energy delta U. So from the first law of thermodynamics, dQ is equal to dW plus du. As dQ is equal to 0, therefore dW is equal to minus du. Minus du means what? The work transfer is equal to work transfer. We are getting the work transfer on the expense of what? Internal energy. So internal energy is reducing and we are getting the positive work output during the expansion process. Similarly, when you are providing the work during the compression, so that work is the negative work and we are getting the increment in the internal energy. So that will be the positive internal energy. So one term is always negative in this particular equation and both the terms are equivalent to each other. The values are equal. So total amount of work energy is converted into total amount of internal energy, and total amount of internal energy is converted into total amount of work energy, as the heat transfer is 0. Thus, the internal energy of the system decreases to produce the work output. Then fourth parameter is the heat transfer. In this process, there is no heat transfer between system and surrounding. So dQ value is equal to 0 and entropy of the system remains constant. And fifth parameter, change in enthalpy. So change in enthalpy for all the gas processes, we are knowing the value, we are knowing the equation, that is equal delta H is equal to mCp T2 minus T1. So we can calculate the change in the enthalpy. As there is a change in the temperature during the expansion and compression, we are getting the change in the enthalpy. Now change in entropy, we are knowing that ds is equal to dq by t. So dq is 0, therefore change in entropy is 0 for this particular process. So these are the 6 parameters of analysis done for the constant entropy process, and we have to use these corresponding formulas to solve the simple numericals on the constant entropy process. So we'll solve the simple numerical on this process. So I will read the numerical first. Numerical number 1. 1 kg of air at 115 kilopascal and 15 degrees Celsius is compressed adiabatically. It may be given in the problem adiabatically or isentropically or compressed by a constant entropy process. So that you have to recognize which type of process is this. So adiabatic process is similar to the isentropic process, or it is also called as a constant entropy process. So it is compressed adiabatically to the volume of 0.1 meter cube. Full stop. Calculate the final temperature and pressure of air, comma, work transfer and change in the internal energy. Full stop. Take capital R is equal to 0.287 kilojoule per kg degree Kelvin and CV is equal to 0.712 kilojoule per kg degree Kelvin. So this is the problem given. So while solving this problem, we are always writing the given data. So you have to mention which type of process is this. So this is the constant entropy process of the adiabatic process. So what is the mass given in the problem? So mass is equal to 1 kg. Now initial volume V1 we have to calculate. Final volume V2 is equal to 0.1 meter cube. Initial temperature T1 is equal to 15 degrees Celsius. So we have to convert that into degree Kelvin. So adding 273 to this 15 degree, 15 plus 273, that is equal to 288 degree Kelvin. Then final temperature you have to calculate T2. Now initial pressure P1 is equal to 115 kilopascal. Final pressure we have to calculate. So find the initial volume, final pressure, final temperature, work done and change in internal energy. So this is the problem which is asked for 8 marks in the examination. Now we are representing this particular problem on PV and TS diagram. So this is a problem of compression process, adiabatic compression. So our state point is located here on the PV diagram. So we are compressing this particular gas up to the state point 2. So during the compression, the volume is decreasing, pressure is increasing, and it is moving along a process curve which is governed by the governing equation, that is PV to the power gamma is equal to constant. So volume is reducing from V1 to V2 and pressure is increasing from P1 to P2. Similarly, on the temperature entropy diagram, we see that temperature is increasing from T1 to T2 at constant entropy. So S1 is equal to S2. So we have to locate the process always on the PV and TS diagram according to the problem, and we have to write down the values of different parameters of pressure, volume and temperature at state point 1 and 2 on the PV and TS diagram itself. Therefore, we can locate which parameter is unknown for us, and we can calculate those parameters and we can move forward to solve the problem. So in the initial condition, so for the first case or the first unknown thing you have to calculate, that is the initial volume V1, because we are knowing the volume V2, that is given as 0.1 meter cube. Our pressure P1 is given, then temperature T1 is equal to 288 degree Kelvin. So T2 we have to find out, P2 we have to find out. So can we find out volume V1 here, because we are knowing temperature T1 and pressure P1. So only unknown here is the volume V1. So at the state point 1 we can apply the general gas equation. So at the state point 1, applying the general gas equation, we can write this equation as at state point 1, P1 V1 is equal to MR T1. So putting the values in this equation, so pressure P1 is 115 kilopascal into V1, that is equal to mass is 1 kg into R value 0.287 into temperature value at initial state, that is 288 degree Kelvin. So V1 initial volume is equal to 0.718 meter cube. So that we have calculated. Then the second point, that is the final temperature, we have to calculate T2. Now we can use the equation, general equation of ratios of pressure, temperature and volume. In that we can equate the temperature ratio and the volume ratio. So T2 upon T1 is equal to V1 upon V2 to the power gamma minus 1. To the power gamma minus 1. So T2 upon T1, T2 upon 288 is equal to 0.718 divided by 0.1. Okay, raised to power 1.4 minus 1. So gamma value is 1.4. Gamma value is 1.4. So we have to calculate the gamma value, that is Cp upon Cv. So you have to first calculate the Cp value, and gamma is equal to Cp upon Cv. So that we have to calculate. Our gamma value is given to you in the problem itself, that is 1.4. So putting the value of gamma, that is 1.4. So we are getting temperature T2, that is equal to 633.63 degree Kelvin. The third point, final pressure P2. So again equating this equation, that is governing equation at state point 1 and 2. P1 V1 to the power gamma is equal to P2 V2 to the power gamma. So we are writing this volume ratios to the inverse pressure ratios. V1 upon V2 to the power gamma is equal to P2 upon P1. So putting the values, so we are getting the final pressure P2 is equal to 1816.65 kilopascal. Now the final, that is the next point, that is the work done. Work done formula we are knowing, P1 V1 minus P2 V2 divided by gamma minus 1. So putting the values, we are getting W is equal to minus 247.73 kilojoule. Why minus term we are getting? The work input is always considered as a negative term in the sign convention. So we are getting the minus value here in the formula itself, in the problem itself. Therefore, the next parameter is the change in internal energy, delta U. So we know that by first law, dq is equal to du plus dw. Now dq is equal to 0. Therefore, minus du is equal to dw. So minus du is equal to minus this value. So internal energy equal to work transport in case of the constant entropy process. So minus du is equal to minus 247.73. So it becomes plus 247, absorbing the negative sign. Therefore, we are getting the positive value of internal energy. So what is the meaning of this positive value? So when we are providing the work energy into the system, that work energy is converted into totally into the increment in the internal energy. Therefore, internal energy is increasing. So that is the positive. Internal energy is increasing. And the work energy is input. That is the negative term according to the sign conventions. So these are the values which are asked in the problem. So we have solved this problem. The only thing you have to note down here, that you have to add in the problem itself, that gamma is equal to 1.4 here. So that is not mentioned in the problem by mistake. So you have to write down in this problem itself, after CV value, So write down gamma is equal to 1.4. Now how to calculate the gamma if it is not given? So we are knowing the formula to calculate gamma. So gamma is equal to Cp upon Cv. Gamma is equal to Cp upon Cv. What is Cp? Cp is the specific heat at constant pressure of that particular gas, and Cv is the specific heat at constant volume for that particular gas. So the ratio of Cp upon Cv is nothing but gamma. So gamma value either you have to calculate from the given data, that is if Cp and Cv values are given, so you have to calculate a gamma term, or gamma value may be readily available in the problem. So you have to find out this particular gamma value and then use in the problem. So this is a simple numerical you have solved on the constant entropy process, and you have to solve some more problems on adiabatic or the isentropic expansion and isentropic compression. Okay, so you solve more and more problems for practice. So thank you. We'll see in the next lecture about the last process in this particular chapter, that is on ideal gases. That is, the last process is the polytropic process. So we'll see that in the next lecture. So thank you.